Hey everyone, we are the Boogie Chassis Team, and this is our team. I'll hand it off to Christian to talk about rapid transport networks.
The Spartan Superway project is a rapid transit network that plans to revamp the public transportation system to fit our modern time. The team plans to accomplish this by implementing various new features that will improve on previous transportation systems designs. The project goal is to develop a publicly accessible pod network that is suspended in air, autonomously controlled, and powered by renewable energy. Our team differentiates from other current public transportation systems, and some key characteristics are the offline stations, which allow convenience for users, nonstop traveling, allowing quick and easy convenient trips, on-demand pods, making sure that pod availability is available for any consumer, and solar-powered systems, which have many environmental benefits. The Spartan Superway project is made up of 4 teams. The Boogie Chassis team, however, is vital to the project's success, as the chassis' role is to be the skeleton and the main support system of the vehicle. As the base of the movable pod, the chassis should be able to withstand the vibrations and forces in dynamic conditions. And this semester, our team will be prototyping and fabricating the chassis, as well as making sure it satisfies the needs of our goals as well as the other team's goals. Next, I'll hand it off to Hussein to talk about specifics of the project.
Our project is to create a bogie chassis that carries its energy supply and operates under wireless control while withstanding a designated load on the scale model guideway. More specific tasks can be divided up into 4 different categories, such as mechanical design, sensor, power systems, suspension. These 4 categories that the bogie chassis project is separated in can ultimately help achieve the goals that are embedded with the Spartan Superway, such as being autonomously controlled and solar powered. The picture on the left showing a bogie chassis on a guideway with a carriage suspended below is the ideal end goal for our project. The picture on the right depicts mechanical design and components that go into a bogie chassis. These components are important to use when designing our bogie so it operates towards completing our 4 categories. This semester, our team will be solving problems revolved around revamping and troubleshooting the design to make sure it fits the needs of our goals as well as other teams. We have started manufacturing our parts and will soon start testing our prototype, as will be shown throughout the current design and fabrication slides. I will now pass it on to the mechanical team to introduce where we are in our design process.
In order to determine the motion of the bogie on the track, a motion analysis was required. After several issues, the motion analysis was unable to be performed. As an alternative, we created an animation to determine how the current bogie will perform as the bogie travels through the straights and curves of the track. When performing the animation, as the bogie goes around the curve, we can see that the 2 outer wheels will lose contact with the track. However, we are confident that the new switch design will solve this issue in order to have the bogie switch and remain on the track. Another contingency we decided to take based on the unsuccessful motion analysis are that the bogie will be manufactured in 3 different stages for the bogie chassis to avoid any major flaws before manufacturing the bogie out of aluminum. In addition to visiting the design center to ask the mentors with help with the motion analysis. The first stage will be to build a bogie from wood, then 3D printed, and lastly, aluminum. This is an overview of our fabrication process since the beginning of the semester. In January, we reevaluated our current design and addressed 2 major issues, track compatibility and an internal stability. After addressing the issue, we started fabrication of the prototype throughout February and plan to complete it by March 10th. Once completed, the electrical and mechanical team will come together to begin testing. Based on our test and possible iterations of our current design, we plan on beginning fabrication of the metal chassis by March 31st or early April. Next, Michael will address 2 major issues with the bogie chassis.
In January, we realized there were 2 major issues, track compatibility and turning stability. First, we'll discuss turning stability. In our old design, our team realized that the support for the axle wouldn't be enough to support the bogie when turning. To minimize possible displacement of the wheels during turning, we decided to add 2 supports that will be attached to the axle. Additionally, we reinforced the attachment to the chassis with sturdier bolts. Next is track compatibility. Through our attempt at the simulation, our team realized that the applied load of the chassis is going to cause the suspension link to rub against the 10-meter track. Our solution for this issue was to reduce the thickness of the suspension link from 0.5 inches to 0.25 inches. We believe the reduction in thickness to the suspension link is acceptable since it'll be fabricated out of aluminum 6061 in the final build. Further testing will determine if design needs to be reevaluated. Here is a visual timeline of how our Boogie Chassis concept evolved over time. The current concept version 2 is similar to version 1, but with changes such as removed flanges, an updated suspension system, an updated cage/housing for the electronics with accommodations for switch arm. In addition, the new revised concept includes another connection and support connected to the axle to provide greater stability and reinforcement, and a thinner suspension link to provide greater clearance between the link and the track. Next, we'll talk about planning for the fabrication process. Before fabrication, our team realized that there are certain parts of the bulky chassis that were too large for 3D printing. So we went about this issue with 2 routes. One, we can compartmentalizing the larger parts into multiple pieces, or use a combination of wood and 3D printing. To continue forward with fabrication, we decided to use a combination of wood and 3D printing to create the initial prototype. With the amount of supplies readily available at the design center, we determined that wood would be suitable for testing the chassis design until we begin fabrication of the metal build. Next, Max will talk about our process for fabricating the chassis.
The first prototype chassis is being constructed out of 1/4-inch plywood because of its low cost and easy fabrication. The bottom plate was cut out using a table saw, then the angles were made using a file and belt sander. The sidewalls were shaped using the same tools, then glued to the base plate. The angle cuts were not as straight and precise as we would have liked, but it'll work for the initial prototype since the 150-pound load will not be applied in the first round's of testing. For future prototypes, it would be better to find a circular saw which is capable of angled cuts. In order to increase the rigidity of this prototype, aluminum braces were made to connect the base plate and the walls. The braces were made by cutting the aluminum into 3-inch strips with a metal chop saw, then mounting the pieces into a vise in order to be bent to the appropriate angle. 2 holes were then put into the braces using a drill press in the design center and then screwed into the chassis. The smaller components of the bogie design require more accuracy and precision, which leads us to fabricate them using machining techniques and 3D printing. The axles were made out of Delrin using a lathe, and the axles need to be rigid enough to hold the bogie and electrical equipment, and also having a very particular shape in order to have the hub motors mounted on them and them function properly. The axle connecting the link and mount to the chassis were both original designs and 3D printed using ABS filament. The last part, which needs to be fabricated before assembly, is the suspension link, which connects the front and back axles. This will likely be machined due to the lack of access to a large enough printer at the moment. The next steps will be connecting the axles to the wooden chassis using the links and mount shown in the slide. Next, hub motors will be mounted, as well as the circuitry to run them, and an accelerometer to begin collecting vibration data. Here is Christian with an update on the suspension.
In order to ensure a smooth ride, we designed a suspension system consisting of a compression spring and 2 dampers on each side of the bogie. The spring, which is highlighted in orange, will provide compressive support, and the dampers are placed on each side of that spring and are outlined in purple. While designing the suspension system, we considered several configurations involving pre-assembled shocks and self-absorbing dampers, but these considerations were deemed unnecessary for the application, and we ultimately settled on this configuration as it's the most elegant, simple, and economical solution for the amount of vibrations anticipated at this scale. Our current design has these dampeners placed on each side of the spring to absorb any excess vibration generated by uneven track surfaces. And lastly, this design will feature a spring with an adjustable tension, or whose tension will be adjustable by changing the spring length or by utilizing a set screw through the center of the spring. Next, Andrew will discuss an analysis of the suspension design.
In order to properly design the suspension, a vibrations problem was to be created. Using the knowledge from previous classes, we decided to create a scenario in which we had to design around the system in order to find out which damping and spring coefficient was necessary to use. To do this, the suspension system, which was just a simple spring and damper setup, had to be set up into a free body diagram with proper assumptions. First, the problem was flipped in order to have it easier to understand. There were 3 masses in this problem that were taken into account and used as one entire mass. The masses were the weight that the bogie has to hold, the weight of the bogie itself, and the estimated switch arm weight. These 3 weights were then estimated into one final mass. More assumptions are written on the right figure, but most important to note is that we are taking into account a downwards force of gravity accounted for within static deflection, so the problem was done in the state of compression. Also, the problem was cut in half in order to have a simple schematic of just one set of springs and dampers, and lastly, the mass was halved as well. Now that we have the problem set up and all the assumptions, it was time to decide what system to build around. As Christian previously stated, and from visiting the design center, the vibrations anticipated were considerably low. This meant that we don't really need a low damping ratio, but we need something in the middle in order to damp out the condition of the track. This resulted us to use an underdamped system that was more to the stiff side with a ratio of 0.8. The picture on the left shows a study of using the same natural frequency with different damping ratios, which decreases in displacement as the damping ratio increases. Our damping ratio chosen is in between the pink and red curve, which gives us small displacements in our damper for the small vibrations we anticipate. The same thought process was applied to the desired natural frequency. Using a frequency of 3 Hz or below would provide a large displacement within the system, so it was desired to use a value of around 4 to 8 Hz. Our team desired to go with 4.5 Hz in order to adequately create a system that has a damping ratio and natural frequency that are both desired. These are the 2 constraints that we will design our system around. Finally, from using the constraints to build around and the assumptions taken for the problem, the coefficients were obtained. Keep in mind that this is only for one side of the system, so these numbers will also be used for the other side of the suspension. To validate these values for spring and damper coefficients, an additional simulation will be required. This way, we can test these values obtained and make any minor adjustments or corrections if needed. This simulation will use more forces instead of just the mass, such as body inertia, pitch, and changes in height. This way, through using the MATLAB Simulink suspension simulation, we will get a better idea of what final adjustments we will need to make for our system when we move on to prototype testing. I will now hand it off to the electrical team to discuss the progress in fabrication.
So during conversations with the mentors in January, we shifted from the single 6S LiPo battery to 2 custom 18650 battery packs, one for the switch arm and then one for the 2 front motors and remaining circuitry. We'll be manufacturing these using nickel strips and a spot welder. We prefer to use these because they have a customizable design and they also have a faster charge and discharge rate compared to the 6S LiPo. So the following battery schematic was created for the 2 front motors and most of the remaining circuitry. It's an 8S 2P schematic. It runs at 30 volts and is able to power the whole thing for a little over 20 minutes. The second battery schematic is for only the switch arm. This is to ensure that the power does not fail during switching. It is a 6S 2P schematic. It'll run at about 22 volts, so it won't burn out their controller, but also provide adequate power to continue switching. Now on to Devin to discuss IMU and the Grafana.
Data for the bogey's velocity, acceleration, and tilt will be gathered and displayed on a Grafana dashboard. The Grafana dashboard is an easy-to-use user interface that is able to get live updates. Grafana is used in conjunction with InfluxDB. To connect to InfluxDB in Grafana, the dashboard link, server URL, and server name are defined as seen in the code on the left. Using the InfluxDB header file, there's a class called InfluxDB client, which allows you to create an object with the parameters of the server name and URL. In the setup, we use the pointDevice function to point to a specific folder. Here we have it pointing to a folder called IMU censored data. After doing that, we use pointDevice.addFile or add field to create a new field for velocity, acceleration, and tilt in the IMU censored data folder. Once all the fields are done, the data can be sent to the server using influx client.writePoint. In the dashboard, we can select individual fields that we created and display it. We have successfully displayed raw accelerometer and gyroscope data on Grafana and can update it every second. Next, Hussein will go over MQTT.
Our base for constructing the architecture of an MQTT protocol are connecting it to the server and defining roles of each component connected as a subscriber, publisher, or both. Communication is performed by creating a topic and sending serialized JSON files to the server, which are created using the Arduino JSON library and stored in specific bit value static JSON documents. The same library is used to deserialize these messages to obtain the value for each key, which in turn controls the motor functionality over IoT using MQTT. The current status of this work is that the serial monitor allows a singular ESP32 chip to publish signal imbued JSON files to the server and then resubscribing to callback required message. The next goal in this code is to be able to send messages between multiple ESP32 chips over MQTT and run the specific microcontroller operating the motor without it being connected to the computer. I will now pass it on to Jake, who will talk about our LiDAR system.
We decided to shift away from using the VLP16 for a variety of reasons. The main reason was due to its cost. The team was not willing to attach the VLP to the Boogie due to the risk of it breaking. Instead, we used the same software we were going to use on the VLP16 on an RP LiDAR A1. The main loss from this decision is that we can no longer collect 3D data. To that end, we have successfully implemented HectorSlam, which allows us to map the track room without using odometry. To use the data we will collect using HectorSlam, we will run a version of AMCL. AMCL is a probabilistic localization system for a robot moving in 2D space. It implements the adaptive Monte Carlo localization approach, which uses a particle filter to track the pose of a robot against a known map. AMCL takes in a laser-based map, laser scans, and transform messages and outputs pose estimates. We have generated a laser-based map already using our HectorSlam implementation. AMCL uses the map we generate using HectorSlam to localize the Boogie within a space. We will be able to get our position relative to an origin that we decide. By using AMCL, we skip errors that occur using dead reckoning and odometry. To power the algorithms, we're using a Raspberry Pi 4. The Raspberry Pi 4 handles the HectorSlam algorithm sufficiently, and we've been able to repeatedly generate laser-based maps. We are currently working on integrating this into our current build. Now I will pass it off to Max to talk about mechanical cost.
The most expensive component on the mechanical side for our budget is going to be the aluminum 6061 sheet that we'll use as the base plate, as well as some of that sheet will be used in fabrication of the suspension links and possibly even the axles. The cost will still remain in the $300 range. And next, I will let electrical team talk about their bill of materials.
On the electrical side, we have three sort of expensive components. It's the two motors, the new batteries from Panasonic, and then finally the LiDAR. We're looking at around $500 total for our build of materials for electrical. Now onto the dependencies. So we sort of have three critical dependencies that we're looking at. The first one is, of course, the charging station, just to ensure that we have adequate ports that they can sort of plug in to do their charging, or how they want to just sort of interface with our battery. Of course, if that doesn't come to fruition, we're going to also ensure that the new battery packs are removable so we can charge them sort of outside of the chassis. The second is switch arm design, since I know that that was a little bit under construction recently. Just want to make sure that the weight and the mechanical fabrication of it, it will still sort of easily fit onto our bogie, and that it won't be too heavy, that it'll sort of bow under the weight of it during the final use. And then finally, the spot welder for the battery manufacturing. We are waiting to sort of get a word back from the mentor team on when that's coming in so we can get to work on actually manufacturing the batteries. Now on to Michael to discuss the Gantt chart.
This is the current team Gantt chart. We are approaching our halfway point for both teams, and based on the number of completed tasks, we are expected to finish on time. Next, I'll go more in depth on the progress of the mechanical team. So during the time of this presentation, there are some tasks that we have completed and are working towards. On the mechanical team, we are collectively on track to fabricating the Boogie Chassis prototype. As we approach the start of March, we plan to have the prototype ready for testing. Through testing, we'll have a motion analysis of the Boogie chassis and different iterations leading up to the fabrication of the metal build by early April. Next is the electrical team.
For the electrical team, we have started testing software and circuit design. MQTT is currently in development. Sending and receiving simple messages has been achieved. Circuits for power distribution board is being designed and tested on breadboards before finalizing the PCB design. The new batteries will be fabricated when we get access to a spot welder and will be tested with all electrical components. As for proximity sensor, there has been a transition from Velodyne VLP16 to the RP LiDAR A1, which has Hector Slam functional. All tasks are currently in development and look to be completed by mid-April. This concludes our presentation. We will now take any questions.